Hello everyone, we are Team 21. Today I'm going to present the topic on unsupervised phenotyping via tensor factorization. I'll start introducing my team and myself. My name is Yu Xiao, and we have Lin Zichen, Li Xingyan, and Xiguan Liu as a teammate. And our instructor is Dada Shan. Our team mentors are Ivy and Xinzhe Wan. In our agenda today, we'll go through some introductions and motivations of our project, and then we'll discuss result of the copilot and some machine models, and also we have some discussions on our observations, and then we will end with our conclusion. To start, nowadays there are a lot of medical data being released to the public for the data analysis, such as EHR, electronic health record. Those EHR data contains the patient demographics, diagnosis, procedures, and drug prescriptions. To dealing with those noisy data and interpret them to the meaningful way are always challenging because from historical research, most of the experimental variables rely on the medical experts' domain knowledge. And because applying phenotyping algorithm tensor factorization model to conduct prediction tests always require meaningful interpretations, hence we will introduce COPA. COPA stands for Constrained Paragraph 2 for sparse and large dataset. It is a method that's based on constraint paragraph 2, which carefully incorporates the optimization constraints such as temporal smooth sparsity and non-negativity in the result factor. The method can efficiently model treatments across a set of patients with a varying number of medical encounters over time. And then here just the chart that illustrates the constraints imposed by COPA on paragraph 2 model factors targeting temporal phenotyping via EHR data. So for our input data set, we actually using the eSIM proof data released by CMS, which is the Center for Medicare and Medicaid. The data set is based on 5% randomly sampling actual Medicare claims data from 2018 to 2020 with the beneficiary identity information masked. And we actually to construct the sparse metrics, we have going through some data selections and pre-processing. First, we are filtering the patient with 4 select SP codes, which represent by 4 disease, and then we are transforming ICD-9 diagnosis and procedure codes to clinical classification software codes for mapping. And then for the cohort in construction or feature engineering, we are assigning the mapping IT to each patient along with the medical features, and we're using the patient visits and various set of medical features to construct the sparse metrics as part of the input for COPA. Here, just a summary of the data set that the stats that we have, and then we have around 34,296 rows patients in total after the filtering, and then in total we have around 19,000 CSS code to ICD-9 mapping, and then we have 516 features in total, and the average visits per patient is around 12, and finally the most important, the sparse metrics, we have around 34,153 row records. And as part of the process, we are tackling this project with some proposed method. First of all, the COPA model conversions. Since the COPA was originally developed in MATLAB, and to best suit our need, we are converting it from MATLAB to Python. And then we perform the ETL on the CMS data, which discussed earlier. We did some data pre-processing and data transformations. At the end, we are using the output metrics from the COPA to create a machine learning model to conduct the prediction task. So in our cases, we are using Apache Spark for the settings, and then using Python version 3.6 along with the PySpark library and Spark SQL to do the ETL. And then logistic regression is the model that we use to do the task, and lastly, we will evaluate the fit time and accuracy for the model output result. And COPA actually offers two functions, COPA and smooth COPA, where smooth COPA has smoothness applying to the UK vector matrix. So both COPA and smooth COPA algorithms are tested in our paper. For each algorithm, we have tried a set of feature numbers which represent by factor of R. In this case, we have tested for R equal to 4, 6, 15, 30, 60, and 120. And for the presentation purpose, we only display the difference between 4 and 15. As you can see in here, it's enough to display that as the number of R increases, the membership of each features in the phenotype actually increase because it has more it has more phenotypes that we can cluster those features into. And then we also have plot the feeding time and chart to demonstrate the feed and conversion time for both algorithms. COPA returns much better feed than smooth COPA for all feature member, and then we have tested all feature number tests. However, for most feature number cases, smooth COPA takes a shorter time to converge, while COPA's conversion time is much longer. So when increasing R, both COPA and smooth COPA need more time to converge and return higher feeds. And we also have plotted the phenotype magnitude using the UK to illustrate what UKs look like. We have taken the patient ID of 12095 in the patient list as an example, according to figures that when R equals to 4 and then the corresponding UK brand returns by smooth COPA changes slower and it has much less spike than the UK from COPA. And when increasing R to 15, the UK from smooth COPA becomes more volatile and less smooth. And to access the predictive power of the phenotypes generated by COPA, we have built a multi-class regression model using the W matrix generated by COPA. And then here's just some model outputs for COPA and smooth COPA in their own heat map form. Now we the heat map that shows the confusion measures of the predictive result versus ground truth. We included 4 groups of patients with different chronic conditions such as heart failure, depression, etc. And the chart indicates that higher number of features we decompose, the better prediction results that we have. And of course, throughout the experiments, we have seen a lot of variance with factor R, and our test results have shown that R shoots the best when R equal to 60, and the benefit of increasing R decrease when R is beyond 120, along with the increasing computing time of the algorithm. So it becomes much more expensive to compute when R has heavily large than 120. And COPA perform much better than COPA smooth even when the number of features are increased. However, the time of COPA smooth is relatively shorter compared to COPA as it adds smooth constraint to the dataset. And feature under each phenotype has a unique feature decomposition. However, we do observe some features that have a little participation in all phenotypes. Is because that those features are mainly procedure features which are underrepresented in the sample data. It occurs when increase the R, we will see in more when the R increases, we'll see more sub phenotype display in the final result. So again, to the interpretable and meaningful tensor factorization models are always desired within the big data world, especially when it comes to the healthcare industry. COPA has certainly fit into the need of it by introducing the constraints such as sparsity, non-negativity, and smoothness to the process, and it improves the interpretability of tensor factorization approaches. And as Python become more popular and desirable language in the data science world, and the Python interpretation of COPA can be easily used to suit any needs to perform phenotyping and tensor factorizations on a large dataset. Moreover, it can help reduce the workload for data science by skip the process of switching from MATLAB to Python. And we are confident that in the future, when phenotyping the noisy raw data, medical data, COPA can be a great big data technique to suit the need. Above, I concludes our presentations, and then we'd like to thank you, our TA, Shinja and Ari, for all the help throughout the process. And we will now open the floor for any questions. Thank you.